Hello, this is Mr. Craig, and this is technically the last lecture of the year. If I make any videos beyond this point, they'll all be for review for the AP exam. But a good way to finish off the year. Starting off with the first thing here, it says like dissolves like. Whenever we discuss or talk in the future about if something is going to dissolve in something else, we have to use this type of term that states that like dissolves like. In other words, if I'm trying to, I'm a painter for some reason, and I use oil paints to paint a picture, what I don't want to try to do is go to the water fountain or to the sink and try to clean off my paintbrush with water, tap water. Because again, an oil-based paint is a nonpolar substance, and the water is a polar-based substance. And this statement, like dissolves like, plays true to heart because all the water is going to do is just simply run off of it. However, if I want to dissolve some oil paint from the paintbrush, then I need to get something that is also the same type of compound that the paint itself is, and that's something like turpentine, paint thinner, even gasoline, but I wouldn't recommend that you use gasoline to clean off your paintbrushes. But it's a nonpolar substance that helps to remove or dissolve another nonpolar substance. So like dissolves like is pretty important. If I try to dissolve any nonpolar substance in water, it simply is going to fall to the bottom or float to the top, one of the two. It will not dissolve or dissociate in that type of medium. All right, colligative properties. Some of the colligative properties, one of the things that we're going to talk about today is molality, dealing with boiling point and freezing point changes. Typically when we talk about boiling point, we talk about boiling point elevation and freezing point depression. That goes hand in hand when you place substances within water that actually has a higher boiling point than water. If you stick something in water that has a lower boiling point, like an alcohol, that typically causes the boiling point to be decreased. The nice thing is, or the good news about the AP exam is they rarely discuss topics like that. So anytime that we do a boiling point elevation or a freezing point depression, we're looking or using substances that have a higher boiling point than water. So it'll always be an elevation or a freezing point depression. And also those constants are on your equation sheet, and we'll definitely take a look at that here in a moment. Let's start off with talking about boiling point elevation, and the equation that we'll use is right here, and it looks a little cleaner on your equation sheet where we have delta T sub B, and the B represents your change in temperature of the boiling. I is a Van Hoff factor. Now we'll talk about the Van Hoff factor when we do some of the examples, but it's a dissociation factor. And one thing that dissociates is ionic compounds. If we have an ionic compound or an electrolyte, that's another common term that's used quite a bit, then we want to look at the way that this dissociates so that we can determine the Van Hoff factor. And we'll do that in the calculations. The Kb is a constant. There's another K there for you. And then the little m is molality. And molality deals with the number of moles per kilogram of your solute. So we'll have moles per kilogram. Now again, we always want to know the mass, total mass of the solvent, and so the kilograms deals with the solvent, and the moles deals with the solute. So how much of the stuff we're dissolving is a solute, and the stuff that's doing the dissolving is the solvent. All right. And I did give some examples here where I had some sodium chloride, when placed in a polar substance, will dissociate into sodium and chlorine ions. If I started off with 1 mole of sodium chloride and place it into, say, water, then I get 1 mole of sodium, 1 mole of chlorine, for a total of 2 moles of particles. So my Van Hoff factor in this case would be 2. If I look at the next example, where I have sodium phosphate, if I take 1 mole of that and place it in water or another polar substance, I'm going to get 3 moles of sodium ions and 1 mole of phosphate ions, for a total of 4 is my Van Hoff factor. Now, one thing that we have to consider, and this is kind of silly when you think about it, but it's not the size of the particle that helps to increase or decrease the temperature which something boils or freezes at, but it's the number of particles. So the Van Hoff factor plays a large role that, say like if you're trying to figure out what salt would be the best salt to use to place on the road to help lower the freezing point for the water so we can melt all this ice in the wintertime, you typically want to pick a salt that has a high Van Hoff factor because that will help lower the freezing point even more effectively. And I know that some salts that are used on the road are sodium chloride. Here lately, there's been quite a bit of use of calcium chloride. And the Van Hoff factor for sodium chloride is 2, where the Van Hoff factor for the calcium chloride is 3. And again, we would definitely show the dissociation of that type of reaction to help determine what the Van Hoff factor is in figuring these problems out. Also, looking at the freezing point depression, same thing. We have the Van Hoff factor, a different constant. Molality is still the same thing, moles per kilogram. So we're looking for the change in the temperature. And in this case, again, the delta deals with the change. So we have to know what the temperature is that we're starting at. So if we're looking at a freezing point, then water freezes at 0 degrees Celsius. Please don't use Fahrenheit. And if we're looking at boiling point, then that starts at 100 degrees Celsius. And I know that on the equation sheet, it has for your constants, like Kf or Kb, it has it in Kelvin, kilogram per mole is our units. If you want to use Kelvin, that's fine. Just recognize that you need to add 273 of this and 273 of that. But do realize that the Kelvin scale, the Kelvin scale, and the degree Celsius scale ratchet up the same. They have the same scale. They just start at different places. So if I increase the temperature of this room by 20 degrees, I've increased the temperature of this room by 20 Kelvin. Now, what's the final temperature? Well, it depends on where we started for each respective scale. All right. Let's go ahead and try some of these problems. Now, I put on here a table that has different K values and different freezing points because, again, you may be asked to later on, not necessarily on the AP exam, but later on in your chemistry career to determine new freezing point and boiling points for things other than water. Now, again, we do have the values for water on here as well, but there's some other things on here. So you may want to hang on to this table, especially for the homework. You may have some questions like that. All right, well, let's get to example number 1 here. Let me see if I can space this out a little bit. Give you guys some room here. So I'm going to expand that out a little because I write a little bit bigger, and I know you guys complain about how much room I don't give you. So I'm apologizing in advance here. All right, so question number 1, or example number 1 says a solution is prepared by dissolving 4.9 grams of sucrose in 175 grams of water. Calculate the boiling point of the solution. And then it says sucrose is a non-electrolyte. Now, non-electrolytes are things that will, let me get my pen back here. Non-electrolytes are things that do not dissociate. A better way to say that is it's a molecular compound. So things like sugars, how can you recognize electrolytes? Well, they typically have carbon in them, or simply all nonmetals. So if you see something that has carbon, you are looking at an organic compound or a non-electrolyte, which means that even simpler, that the Van Hoff factor is equal to 1. So that really cleans things up when you see that, hey, we've got this non-electrolyte. Now, I think I have seen on the AP exams where it actually says that this thing is a non-electrolyte, but don't count on it, okay? Don't be so dependent that you're like, okay, I think this is a non-electrolyte, or I'm hoping that the question tells me. You should be able to recognize ionic compounds from molecular compounds. All right. So looking at question number 1, again, we read that, so let's go ahead and do this. We know that we're going to boil. I'm going to scoot that down so that thinking thing doesn't pop up again. So we have 4.9. Ooh, what happened there? Oh, my pen. What the heck? Hang on. Sorry, guys. All right. So we are boiling. Oh, sorry. Wrong one. So we are looking for the new boiling point. So we have to first of all find out what our change in temperature of the boiling is. So I, KB, M, and again, the I here is 1 because we have a non-electrolyte. Makes that raw very, very easy. Since we are using water, the constant is 0.51 degrees Celsius kilogram per mole. And again, we'll talk about that weird unit. But again, if you don't have that memorized, definitely is right here on the chart. Or it's on your equation sheet. And I think I'd rather you find it on your equation sheet before you find it on this table. And then the molality. Now I'm going to do a separate equation here, but I don't think I have enough room to put that on there. I don't think so. So I'm going to do it off to the side here. So molality again is your moles per kilogram. And anytime you have a mass of water, that's your solvent. So that will go on the bottom, the 175 grams of water. And if you need to identify that that's water to keep you out of trouble, there's nothing wrong with that. We have 4.9 grams of the sucrose. So what we need to do is change that into moles. I'm going to work on the sucrose first, then I'll work on the water. So the sucrose, C12H22O11. And if you get a chance to take organic, you'll have fun with this, and hopefully you'll memorize it. I know that glucose is 180, but I don't have this one memorized. So bear with me. 11 times 16. So 342. It's a big one. It's a big sugar. It does taste good. And these are the natural sugars that are in. I'm going to be quiet on that. I'm thinking of fructose. All right, so we've got our moles of our sucrose, and now I want to get the grams of the water changed into kilograms. So since I have the unit grams, I'm going to convert those grams into kilograms. Okay. And this will give me my molality. And the grams of the sucrose cancel out, the grams of the water cancel out, and I'm left with moles per kilogram, which is nice. So let me figure this out. So times 175, I have my number for the glucose, or sucrose still in, times 4.9 times 1,000. So I get, hang on here, that doesn't seem right. Tag on it. Sorry guys. Divided by, I think I typed in the wrong mass. I wrote it right, but I typed it in wrong. 296. Alright, there we go. So 0.0818, and that's that is moles per kilogram, which is my molality. So I can plug that in up here. Now, the reason why that constant has a goofy unit where it's degrees Celsius kilogram per mole is so that the moles and kilograms cancel out. So if you're careful, let those units talk to you and tell you that you're doing it right. So now I have the unit degrees Celsius. So that number's in my calculator, so times 0.51. So that changes the total temperature by 0.0. Let me do it down here. Changes it by a total of 0.0417, and that's degrees Celsius. Now, that's my delta T. That is not my final temperature, and that's my boiling. So the temperature of the water was elevated by that amount. In other words, it elevated the boiling point, in which the temperature in which the water will boil at. So to finish this, make sure that you know what the temperature is that your substance, in this case water, boils at. So that's my boiling point. And then I added this 4.9 grams of sucrose, which is not a whole lot. I mean, remember that that's not even close. Wow, yeah, that's really small. All right, so 0.0417 degrees Celsius. That all adds up to 100.01 degrees. Now, again, that's a decimal. So the temperature was increased by a small amount. Not even, yeah, it's really small. So, but again, the key here is that the temperature was elevated by the addition of something. So there was some stuff added to the water, and the temperature went up. All right, let's look at the next example. Calculate the freezing point for water if 320 grams of calcium nitrate is added to 2,500 milliliters of water. So I'm going to use a space from above here to help out. So, oops, calcium nitrate is an ionic compound. So when that dissociates, we get calcium ions, and we also get 2 nitrate ions. So my Van Hoff factor here is 3. Alright, so coming over my delta T sub F, and again, K sub F and molality. That's an I there. So my Van Hoff factor, I go from 1 particle to 3, and again, add up the coefficients, even though there's not a 1 there. So 1 plus 2 is my 3. My freezing point value, I'm sorry, my constant is 0.86, and that's kilograms per mole. Alright, now solving for the molality, I'm going to do that again down here since I know I'll run out of room. So I have 320 grams of calcium nitrate, and that's going to go over 2,500 milliliters of water. Alright, so let's change the calcium nitrate into moles. So let's see, 40.08 plus 2 times 14.01 plus 6 times 16. So 164.1 grams per mole is my calcium nitrate molar mass. Alright, so now I need to get these milliliters of water to kilograms of water. How am I going to be able to do that? Well, think about density of water. Density of water is, I don't want it right there. Do a little side note here. Density of water is equal to the mass over the volume. Okay, and we know that the density for water is 1 gram for every centimeter cubed, or 1 gram for every milliliter. So, knowing the density of water, we can actually solve for this. Now, you're required to know what the density of water is. So don't be looking on a chart to try to figure out, well, what's the density of water, and why is he making us know this? Okay, so now, if I cancel out my units there, I have my grams. So now I can convert that to kilograms. So again, remember that there's 1,000 grams in a kilogram. And let's get a value for that, which I'll just put it right up top. So I've got my mass down on the bottom, 2,500. Okay. And then take the inverse of that, times 320 times 1,000. So, whoa, that's not right. Man, this calculator is not behaving well. Sorry, guys. 2,500, 1.64. 0.78. Boy, I'm still not having fun with this. Sorry. 1,000 divided by, I wonder if these buttons are all going down, times 164.1. Alright. Says that the is 0.780, and that's moles per kilogram. Okay. Now that should give us a nice value here, times 1.86 times 3, 4.35. So 4.35 degrees Celsius. So that's our delta F. I know we're running out of room here. So that's my change in temperature. What temperature do I freeze at? Well, water freezes at 0 degrees Celsius. So minus 4.35 degrees Celsius will give me a new temperature of negative 4.35 degrees Celsius. Now, again, I know that's pretty elementary, and we might think, wow, why does he need to show, or why do we need to show that? Well, if it asks for you to calculate the new freezing point for a substance, regardless of how elementary it seems to you, show it. I guarantee it'll be worth a point if it's asked on the AP exam. All right. One more example, and hopefully this isn't taking too much time here. It wants you to calculate the freezing point and boiling point for chloroform, which is polar, if 75 grams of lithium phosphate dissociates in 100% dissociates 100% in chloroform, is placed in 23.2 mole solution of chloroform. Alright, so we're going to do the freezing point and boiling point. But before we do that, let's figure out what the Van Hoff factor is. So 3 lithium ions plus phosphate. And again, phosphate is a polyatomic. Polyatomics act like molecular compounds. We're not going to break those down any further. So the Van Hoff factor here is 4. Okay? So keep polys together. Never ever dissociate the polys. Okay? Only the metals that come with the polys or the non-metals, depending on what we're looking at here. Alright, so we'll start with the freezing point. And so we'll go freezing. So the Van Hoff factor, KFM. Now, I don't think I said this in the other problem, but the Van Hoff factor is specific for the solute. The KF is specific for the solvent. And so is actually the molality is for both, the solute and the solvent. Okay, so the solute solvent and the solute solvent for both. Okay, so I don't know if I said that earlier on, but let's go ahead and get going here. So the Van Hoff factor is 4. Now, since we're using chloroform, we're going to have to look at the value for the freezing. So the KF for chloroform is 4.7. Now the units are the same, but oops, whoa, I went way past it. So 4.7, is that right? 4.7? Sorry. Yeah, 4.70. Alright, so 4.70, and again that's degrees Celsius, kilogram per mole. And we still have to do the molality the same way, so there's nothing wrong with that. Actually, let's be smart about this. Let's calculate the molality one time, and then we can use it for both. So the molality here is, we have 75 grams of lithium phosphate. Okay, and that is dissolved in, now this is interesting, 23.2 moles of chloroform. Huh, okay. I like this. Opportunity for problem solving. 23.2 moles. Alright, well let's work on the lithium phosphate first, so we know we need to convert that into moles. Alright, so 6.94 times 3 plus 30.97 plus 4 times 16. Alright, so 115. The molar mass for lithium phosphate is 115.79 grams. Okay. Alright, so now if we stop right there, we've got our, let's do this. So now, if I stop right here, this part right here is my mole amount. However, I need to figure out, let's go with a different color on this one. Is that elbow? That's not bad. Okay. So, now what I need to do is, for my chloroform, get that to kilograms. So what I need to do is move the unit moles up. So in 1 mole of chloroform, which happens to have the equation CHCl3, how'd I know that? Yeah, the table told me so. So there's CHCl3 here. Okay, so that's my chloroform, which is a pretty simple compound. We have to find out what the molar mass of that is. So again, 1 carbon plus 1 hydrogen plus 3 chlorines. And that gives me a molar mass of 119. Yeah, come on, 119.368 grams. Okay. So now I've got my moles converted into grams. Now all I have to do is convert the grams into kilograms. Okay, and that'll give me a mole, a molality value, which I like because now we have to use this molality twice. So let's type this in and see what we get. Okay, divided by 20.2 times 8. So my molality is 0.23389, we'll say. And again, I'm not trying to round too much here. I don't like to round a whole lot. Alright, so we'll take that number and we'll plug it in up here. So 0.23891, and that's moles per kilogram. Okay. Now give me some number. Let's get that value there real quick. Times 4.7 times 4. So 4.40. Okay. Alright, we'll come back to that in a second. We'll do all those at one time. Alright, let's do the boiling point real quick. Let's get the pen back to a normal color. Alright. So, boiling. So T sub B, I, K sub B, molality. Again, Van Hoff factor is 4. Now the K sub B is a little different. So 3.63. How'd I get that? Right there. 3.63. Okay, so 3.63. If I say it enough, I'll remember it. 3.63 degrees Celsius per kilogram mole. And we just calculated that, so that'll save us a little bit of time. 1 moles per kilogram. Okay. And that'll give us a number. Let's find out what that is. 0.63 times 0.23891. So 3.4. Okay. 0.40 degrees Celsius. Alright, so those are our changes. So our delta T and our delta F are given here. So there's our delta F. There's our delta B. Alright, so now let's do our boiling point. Freezing point first, since that's the first one we calculated. Freezing point, normal freezing point for chloroform is negative 63.5. Negative 63.5. Negative 63. Negative 63.5 degrees Celsius. Oops, big Celsius. And since we are decreasing the temperature there, we will reduce it by that amount. So now it'll be a 66. I think that's right. 0.9 degrees is the new freezing point. And what's this one up here? And then the boiling point 61.2. 61.2. Yeah, 61.2. Boiling point 61.2. And oh, darn it. Hang on, I'll come back to that one. I did the wrong one for that one. So positive 3.4. Sorry guys, I see my mistake. Alright, so that one's that's an elevation, so that'll be 64.6. Let's fix this over here. Use the boiling for that one. We don't want to do that. Let's use the freezing. Oops. So that was the freezing was the delta F, 4.4. Okay, I was like, what? Alright, 4.4. So that probably means I need to change that number as well. Okay. Alright, so negative, we need to subtract that. Come on, right. So negative, we're going to subtract that, so negative 67.9. Okay. So, correction. There's our new freezing point after I added the correct value in there, and there's our new boiling point for chloroform. I hope this video has helped. I know this was a little lengthy. Apologize for the length of this video, but I do hope it helps, or helped you. And if you have any questions, please don't hesitate to email me.